Gases. In many respects, this is my favorite topic for a number of reasons. One is, historically speaking, modern chemistry started with gases. Primarily because under certain circumstances, all gases behave alike. So it really didn't matter what gas you had to investigate, you could get the same results. Now that's in physical terms, of course. Gases are still chemically based, so they can react with one another and if you put the right gases together. But initially, gases were investigated for their physical behavior. And we're going to look at gases in terms of what a gas is and then how it behaves. And that means we're going to investigate gas laws before we get to theories as to why they behave the way they do. Okay, what is a gas? The particles in a gas are largely independent. We say they're semi-independent simply because we're hedging our bets. Gases tend to behave as if they were just billiard balls. They're so far apart and they're so small relative to the distances they travel that, and they're moving so fast that when they strike one another, it's just like they bounce off, which is probably why all gases behave similarly in physical terms. Okay, I said they're rapidly moving, and they could be composed of atoms, like noble gases, or they could be molecules. A molecule of a gas might be something like dinitrogen. It has two atoms hooked together to make the gas. Or it could be carbon dioxide. Okay, so a gas could be composed of either classification. Another interesting characteristic of gases is when you put two different gases together, you always get a homogeneous mixture every time. In other words, two or more gases together makes a solution of gases that we're breathing with right now. Gases do have mass, the particles, which should be obvious because they're made of atoms and molecules, and all those particles have their masses, which means that in combination with their motion means they have kinetic energy. So I don't know if you've ever been introduced to this, but kinetic energy equals mass times velocity squared, take half of it. So every particle has its own kinetic energy. We have to assume that the gases are randomly moving. And the reason we do that is because there's so many of them. Even though they're very far apart, just a small sampling of gas has billions of atoms and molecules in it. And we can't track every one. If we could track every one, then we could say, okay, these two come together and they go off like that. But then we'd need 100 times the supercomputer we've got now to do the calculations. So we assume that their motion is random. That's more for convenience than it is for reality. Okay. So what we are looking for first is how these different laws describing gas behavior describe their workings and how they interact with one another. And we're going to start with gases as ideal. In other words, we know how gases behave in reality. Right? We know we can cool a gas down and turn it into a liquid. Some of them we can cool down far enough and compress them and make them into solids, like carbon dioxide, dry ice. It's a solid gas.
Dry ice.
Yeah, it's carbon dioxide.
Oh, is it?
Uh-huh. So if you take a chunk of dry ice, throw it on the ground, at even today's temperatures, it's high enough to, you'll see the steam coming off of it. It's sublimed. It goes directly from a solid to a gas.
I ain't never seen that or used it, but I've watched videos of like just males and they say don't breathe in the gas.
No, that's right. Don't do that. It's solid carbon dioxide is minus 78.5 degrees centigrade. So it's pretty cold. You can pick it up and move it around in your hand, but if you let it sit for very long, it'll burn your hand. You get,
Is that like close to the reason why salt and ice burn your hand or whatever it is?
salt and ice.
Something like you put something in your hand, you put something else on it with ice, and you just rub around and burn it really bad or something.
Oh, that sounds like the same thing that happens in an ice cream freezer.
Yeah.
When you add salt and ice together, it makes it colder.
Yeah.
Have we done that experiment yet? Freezing point depression?
Yeah, with the thermometer,
And we had,
boiling water, and we mixed ice into it.
no, we haven't gotten there yet. In fact, that's second semester. It's a colligative property that we won't investigate unless you come back for 214. But what happens is anytime you dissolve a solute in something like a liquid, then its freezing point is depressed. So if it starts off as a frozen, then by adding that salt to it, it causes the temperature to drop. That's how you make ice cream. Yeah, that'll burn your hand. This will burn your hand. Liquid nitrogen. Will definitely burn your hand unless you roll it around in your hand.
Motion, right?
But it produces what's called the Leidenfrost effect. I don't even know how to spell it. It vaporizes so quickly that it produces a gaseous layer between the cold liquid and your hand. And gas is a good insulator. So as long as you keep that gas there, it won't burn you. Or if you get some on your hand, all you have to do is slap it and it's gone. Okay. So we need to describe, first we're going to describe an ideal gas behavior. And then we'll extend that into real gases. We'll talk about this a little bit more, gas equations, so we don't need to dwell on that right now. I mentioned we were breathing a solution of gases, which the Earth's atmosphere is necessary for life, primarily because of two things. One is oxygen for air breathers, and the other is carbon dioxide for plants. They have to have carbon dioxide is food to plants. It's not like the EPA says, a pollutant. In fact, there's plenty of evidence out there that the more carbon dioxide you have in the atmosphere, the more productive your plants are. That's been proven, definitely in greenhouses and grow chambers. But now evidence is coming in for field research that's showing increased production from plants based upon an increased carbon dioxide level in the atmosphere. Okay, here we go. Yeah, don't get me started on global warming.
I was getting ready to ask if you were going to get that. Because I remember from last week where we talked about it.
Man. Yeah, I better just move on. Get me up on my soapbox. Okay, so gases can be described entirely, at least their physical behavior, can be described with 4 variables. One is pressure. But you also need to know volume, temperature, and the amount. This is short for moles. If you know those 4 characteristics, if you know those values for those variables, you can describe that gas, and all other gases at those conditions will behave the same way.
I did this in high school, but I can't remember.
So of course, you understand that gases can't maintain their own shape and can't maintain their own volume. So you have to have a 360 three-dimensional container for the gases to study them. And historically speaking, the gases were first investigated in terms of pressure and volume. And I think that's because the technology was there for them to do that. We could measure pressure, we could measure volume easily. Temperature came later. And actually, the quantification of moles came later. Okay, so we needed some way to measure pressure. This Italian fellow, Torricelli, invented the barometer in the middle 17th century. All he did was he took a tube of uniform diameter, which was easily made in those days. The technicians had mastered that skill, and closed it off at one end. And then he filled it up with mercury. Now, why did he use mercury? Well, he needed a liquid to make his barometer. But he found that if he used water, after trial and error, he discovered that water, he'd need a tube that was about 33 feet long. So he said, what if I use something that's denser than water? So he tried mercury. It's the only available liquid metal, and it was readily available. Mercury was common. It was, in fact, some people believed it was beneficial to ingest mercury. But he didn't do that, to my knowledge. He filled the tube up with mercury and then capped it with his thumb and then inverted it like that in a pool of mercury. Right? And when he turned it loose, come on, there he goes. When he turned it loose, it dropped to a certain point and then stopped. So what he had actually done there is created the world's first vacuum, right? Because first there was something there and now there's not.
You can vacuum it up with straws when you drink a bottle.
Yeah. And he noticed that if he watched this over time, just let it sit still, he noticed the level went up and down. And he correlated that with the weather. Bad weather comes through, it would drop. When the weather cleared up and the sun started shining again, the level would go up. So pressure was measured in terms of height of that column. Now we know that, or we accept that 1 atmosphere pressure, that is the air pressure at sea level, on average is 760 millimeters of mercury. In a Torricelli barometer, that's equal to 1 atmosphere. And that's our first conversion factor that we can use for gas pressures. The other thing he did was he took this barometer and threw it in the back of his ox cart, and he went up the mountain. He noticed as he went up the mountain, the level of the mercury dropped. So he associated that change in pressure with altitude. And he reasoned that the reason it was lower pressure was there was less gas pushing down on this pool of mercury. And then he went down the hill and saw that it went up. So now we have a reliable way to measure pressure. Now this is good for air pressure. But eventually, scientists needed a way to use this method to measure the pressure of confined gases. So they created what's called a manometer.
So if you look like Mount Everest, how low would it go?
Oh, I should have known you were going to ask me that question. It's in the neighborhood of maybe 500 millimeters. It's pretty low. But to make a manometer, you need this mercury pool, and then you have your tube, but this has to be sealed off, and then this tube goes over to your container, and that's your trapped gas pushing on this surface here, and then you can measure the air pressure, the pressure of the confined gas. Okay. Let's see. And they've been using that ever since to measure weather patterns.
They still use that?
Well, they use air pressure to judge incoming weather patterns. Okay. Let's see. Come on. There we go. There's normal atmospheric pressure. We have set 1 atmosphere at 760 millimeters of mercury. Now, there are other measurements that you can apply to this. 1 atmosphere is 14.69 pounds per square inch. That is another equivalence. Well, I created these slides in Beckley, so I have to use Raleigh County Airport as my example. If the pressure on a certain day is 694 millimeters of mercury, then at this 2,500 feet above sea level, we can calculate the atmospheres for that also. We just need to say, all right, this is where we're starting. This is our conversion factor. 1 atmosphere equals that much. And we set it so that we can cancel millimeters of mercury and make it 1 atmosphere, or make atmospheres. And it's predictably less than 1 atmosphere because of our altitude. It probably wouldn't be that much of a difference. I think Logan is lower in altitude, probably maybe 1,000 feet above sea level. We're kind of down in a valley here.
Yeah.
Winter Place, which is south of Beckley, I believe. It's a ski resort. They're at much higher altitude, and their pressure is a lot lower. Okay, so you can do these unit conversions, and a lot of the stuff we're going to do with gases involves unit conversions. Okay. There are standards, international standards for pressure, air pressure, gas pressures, and the accepted value is the Pascal, named after a polymath named a Frenchman named Blaise Pascal. You've heard of Pascal's triangle in math class? Yeah, he gave us that one. That's where you start off with 1 here, and then you add these 2 together, makes 2 there, 1 here. Add these 2 together, makes 3, 3, 1, 1. It just expands.
I did that last year.
But he also worked with gases, and this unit of measure is given the Pascal. the thing about this unit of measure is that it is numerically equal to 1 Newton per square meter. Right? So this is a force, and this is an area. So force per unit area is equal to pressure by definition. So this is equal to 1 Pascal. And the thing about that is that you can interconvert. If you use this pressure in a calculation where you need to be able to combine or cancel units, then you need to know this equivalence. Otherwise, you'd be stuck. And it's a derived unit. Right? This is a fundamental unit, the meter. We talked about that early on. This one is also a derived unit, the Newton. It's derived from Newton's second law. Force equals mass times acceleration. This force of 1 Newton is equal to the standard kilogram times the standard acceleration, which would be meters per second squared. Okay, that's 1 Newton. 1 meter per second squared. Kilogram meters per second squared is a Newton. So all these things are interconnected. We're not going to be using the Pascal very much. I mean, it's worth knowing, but most of the calculations we're going to be involved with use either mercury, the height of a mercury column, pounds per square inch, or atmospheres. There's another equivalence. 29.92 inches of mercury is equal to 760 millimeters. And 40, well, I gave you that one earlier. Now, one that's used in weather is actually the millibar, which is just 1,000th of this. So it'd be 101, 101.325 pascals is 1 millibar. And you'll see if you look at any weather maps, you'll find the isobars. You know how they draw the same pressure like that. Then you'll have another one here. So if this is a center of low pressure, this one will be lower pressure than that one. Anywhere on that line would be the same pressure.
That looks like the
Yeah, a similar idea. But they use, the weather maps use millibars. I used to operate a piece of equipment. It was called a lyophilizer, which is a fancy word for freeze dryer. And you put your product inside the container and push the door closed, clamp it shut, and start pulling a vacuum. And I get the vacuum down to like less than 10 millibars. And then you apply just a little bit of heat, and it sublimates the water out of your samples. Okay. So this just illustrates you can convert from one unit of measure to the other. Fairly easily. Sometimes you have to chain them together. Oops. Calculate the atmospheric pressure in pascals. Exerted pressure of mercury column on a 5 millimeter. That should be 5 square millimeter diameter. Oh, 5 millimeter diameter. Okay. So this is just a sample calculation of this is how much mercury I think is in that tube for a given pressure, 1 Pascal. I'm not gonna have you do these calculations, so we'll just pass over that one. Okay, so let's get to the laws that describe gas behavior. Boyle's law is the first one. It's involved with these two, pressure and volume. Robert Boyle, in the middle of the 17th century, started doing experiments with gases, and he was given credit for being the first experimental scientist, because he measured gases. He got quantitative data from his experiments. He was an Englishman, and he knew, based upon the previous experiments and others who worked in the area, that these four conditions had to be controlled some way or other. If you want to let these two vary one from another so you can see how they behave, then these two have to be constant. Okay. So this was easy. All you have to do is trap a gas and don't let any gas in or out, and he had exactly that amount. So he was good there. Temperature, as long as the temperature was reasonably stable, you conduct your experiment over a short period of time, then the temperature is stable. But if you needed to, you could submerge your device in ice water or just water, as a matter of fact, and it would stabilize the temperature.
Yeah, because water is good at staying around temperature.
Mm-hmm. Yep. Okay, so he related pressure and volume, and he found that if he added pressure to a gas, the volume decreased. They were inversely related, and he found that pressure times volume is a constant. So that is Boyle's law. Right there, in simplest terms. Okay.
Why is it constant?
K, that's, it should be a small k, actually. It's constant. I mean, if pressure goes up, volume has to go down in order for the product to be constant. And if you plot the values, well, first of all, let's get the data and then it'll plot as we. Okay, so if you start off with a pressure of 25 atmospheres and 4 liters of gas, then the product there is 100. So in that case, K is equal to 100. So any change you make to one of these, the other one will change to keep that at 100. So if we decrease the pressure to 20 atmospheres, then the volume is going to increase to 5. Okay. Now, how do you do that? Well, in a modern sense, you just take a cylinder with a piston in it, right, and put a certain weight on it, some force that's constant. And then you change the weight on that cylinder. Right? Maybe cut it in half or decrease it by 1/10 or whatever the case may be. And each time you do that, the cylinder moves up and you can measure the volume. Boyle did it a little bit differently. He had what's called a J tube. So he had a tube. Remember, in those days, glass blowing was a highly developed skill. Right? This J tube was closed at one end, open at the other. And all he had to do was put mercury in here. At first, it would just pool in the bottom. He'd put a little bit more, and eventually, he had enough in there to seal it off. And at that point, the number of moles was fixed. Then we talked about temperature. And then as he added this in here, he noticed that when he got so much mercury in here, that over here, it was down there like that, below. And then if we went up here, it only went up like that. So he was adding more mercury in it, but it wasn't moving up as far here as it was here. So something was pushing back. The gas was pushing against that mercury column.
How we know what gas it was?
Didn't matter. No, just trapped
It
air.
was where the pressure. Okay, I understand now.
Yeah, eventually they did put known gases in there, like oxygen was common in those days. So what's the pressure on that gas? Well, it had atmospheric pressure. So we had a barometer to tell them what the pressure was, plus the difference in height here. Okay. And he kept plotting that data, and he found that you got a curve like this. So as the pressure, if we started over here, as the pressure increased, the volume decreased. As you follow that curve, as one decreased, the other one increased. And that's characteristic of this arrangement. Two variables times each other equals a constant, always looks like that. And it produces a curve called hyperbola. Hyperbola. If you remember from math class, a hyperbola will never touch the axis here and will never touch the axis there.
There's a constant just infinitely go on.
Huh?
There's a constant infinitely go on each way.
Yep. Yep, out to infinity. Okay, that's an inversely proportional relationship. So we've got that relationship. Now, how do we solve problems using Boyle's law? Because whenever you change conditions, the K is going to be different. Right? So you don't have it's constant for that particular experiment, but that constant will change. So we found that it was more convenient to look at this in terms of before and after. What are the conditions before? Right? Initial pressure times initial volume equals a constant. And then at the end of the experiment, you would look at final pressure times final volume equals constant. Well, like I said, if you start off with the same conditions and you don't change the conditions here and here, then these two are equal to the same constant, which means they're equal to each other. So that's where we are. You could say like P1, V1 equals P2, V2. And that is the before and after version of Boyle's law that works. Now you don't have to know the constant. You just have to know three of these variables and you can solve for the other one. Here's an example.
Just like variables in math.
Yeah, oh yeah, oh yeah. Uh-huh. Yeah, this is deja vu all over again. So if we have a gas with a final volume of a gas, calculate the final volume of the gas with 15 liters of gas at 500 millimeters of mercury, suffers a pressure drop to 125 millimeters. So it's important to use this for using this expression that you know what number goes where. So you need to set it up. So in fact, it's better if we use initial, final, final. So what's the initial pressure? When 1500 milliliters at 500 drops to this. So initial, it's 500 millimeters of mercury. And initial volume is 15 liters. Okay, now what's the final pressure? 125. Now you know which one is the unknown. And you can plug them into your formula. So if you put them in there in the wrong place, then you get the wrong answer. And let's see, did we do the calculation?
At the bottom of it,
Yeah, well, we rearranged for this one right here.
next time you click, you can color, you're gonna find the answer.
There we go. So you can do it that way. You can rearrange it and then plug them in, or you can plug them in and then rearrange it. Either way it works.
So is that, that's divided by, okay, yeah, divided by.
Right. Because it used to be over here, pressure final, now it's over here. And it turns out that with a pressure drop to 125 millimeters of mercury, now the volume instead of 15 liters is 60 liters. Yeah. And that's, well, actually, I was going to use an example, but it's a little bit different. Nuclear reactors, you know, have those huge concrete, reinforced concrete domes. At least in this country, they do. Have you ever seen pictures of them?
I might have, but it's been a while.
Yeah. Anytime you look at a nuclear reactor in this country, you'll see a huge concrete dome. That's where the nuclear reactor is located. The reason they do that is they're high pressure water reactors. And water under that much pressure can hold heat without turning into a gas. But if it ever springs a leak, that water will instantly flash to gas. And the rule of thumb is liquid to a gas is roughly 1,000 times volume increase. So you get a little bit of water flashing to a gas, you need something big to contain it.
They made a movie on Netflix about that. About what happened if a leak, if water started leaking in a nuclear reactor like that.
Yeah.
Isn't that a different country, but it's like the same concept of what you just said?
Yeah. That, and there's plenty of evidence that the choice to push this country toward high pressure water reactors was a huge mistake.
Yeah, because in that one time, that whole like part of that country had to evacuate.
Yeah.
Or else like everyone would like, because the people who work there, they can't get out, they shut it down, so they didn't care about the people inside, they just like, here they is.
Yeah.
Or they even use what they say, they just got out of there.
Sounds like Russia.
It was like Korea or something.
Korea, okay. All right, so that's Boyle's law. Let's see, this another example. All right. So the principle here is the same as always. If you have an equation that has only one unknown left, you can solve for it. All right, the next one comes along somewhat later. Charles' law. Charles was a Frenchman. Charles was his last name. Yeah.
What's his first name?
I don't remember.
Probably starts-
Louis? Louis? I don't know. Could have been anything. You know, that's a good question. I have to look that up.
French people have unique names sometimes.
Yeah. Sometimes they have two first names and two last names.
It's so weird. It's hard to tell.
So Charles came along later. Let's see, do we have there it is. A little over a century later. And the reason that his investigations of temperature and volume here had to wait, those would be constant. The reason that he had to wait was there was not a reliable way to measure temperature until then. They had various experimentations with, well, I don't know, a Galileo thermometer, I think they call it, with the bulbs that float. I just have one before my cats broke it.
And things for me sometimes. I used to have one. I'd just be sitting there for a snack.
Yeah, I get a screw loose. Oh, read my own slide, Jacques Charles. I guess that's French for Jack.
That's what I was thinking.
Anyway, Charles is given credit for it, but the work was actually published by Gay-Lussac later. Okay, so what did Charles discover? Or what is he given credit for? When you increase the temperature, these two being held constant, you increase the volume. Right? So they're directly proportional, which means that volume quotient temperature is equal to a constant. Because if this one goes up, that one has to go up in order to maintain that constant. So whenever you see a relationship that's supposed to be constant, it's a quotient that's direct proportionality. If it's a product like pressure times volume, then it's inverse, equal to a constant. Okay. So here's what he discovered. Straight line. Okay. And all you have to do to recognize that is, well, this puts temperature down here. I would have put, no, that's right. Temperature is the independent variable and volume is the dependent variable. But if you take temperature and put it over here, what's that look like? It looks like a straight line. Just add your V, you got mx, y equals mx plus b. So that's a straight line. I didn't show you earlier. I might as well do it now. Pressure times volume equals a constant. If we put volume on the other side, like that, now that's a straight line. Only if you take the inverse of volume. That's why the straight line worked in that graph example. If you take the inverse of volume and plot it against pressure, you get a straight line instead of that hyperbola.
So there's a straight line, just continue on, one straight line forever. Yeah.
Yeah, you can extrapolate it as far as you want. Okay. And this is also what, let's see. This is also what Kelvin used to develop his temperature system, right? He took this relationship and he said, what would happen if, at what temperature would the volume be zero? So he just extrapolated that line all the way down till it intersected and found it was minus 273 degrees Celsius.
That's how you go to the equation.
That's the simple version. He actually went into massive detail in terms of heat, what was known about heat laws then and heat engines. And he quoted a couple of world-renowned engineers and scientists to do it. Sadie Carnot was one of them, whose work on heat engines is quoted around the world. Anyway, this is where absolute zero came from. And in order to do calculations where temperature is involved with gases, we have to convert temperature to absolute units. Right? You can get this plot of straight line simply with liters and degrees Celsius. That's true. But if you want to go beyond that to calculate other values and associate them with these other variables, it has to be absolute temperature. You got to have all positives, no negative values, because negative values in temperature will mess up your calculations pretty quick. Like volume is always positive. Pressure is always positive. Moles obviously are always positive, so temperature's got to be positive too.
Well, that stuff only has to be positive. If it goes below zero, if it goes to zero or below, it just can't be there.
Yeah. Okay, so, and we can use a similar reasoning here if we want a before and after equation for solving problems. If you say this is initial is equal to that constant, and then the constant is also equal to final, final, then you can say they're equal to one another, just like we did with pressure volume. And there are several examples here, but I'm running out of time, so I need to move on. Okay, that was Charles' law, and these are some examples. You've got plenty of examples in your review document, and we'll go over those next week in a review session. Okay, let's see, one more. Avogadro's law. Avogadro was an Italian. In the early 19th century. And his work was with volume and moles. So we have to we have to hold this one constant and this one constant and relate these two. Okay, and he found out that as with these constant, as the number of moles goes up, the volume goes up in a relationship that is directly proportional. Okay. And you can do the same thing with this one. Initial.
You can about do that with every one of them.
Yeah, as long as they're equal to a constant, then you can set them equal to each other. Yep. That's not a very good V. There we go. Avogadro was noted also for solving a massive problem that had developed in the scientific community and with manufacturers, companies in Europe. They were conducting, they were generating products using reactions of various kinds. And when something went wrong, they had no clue how to fix it because they didn't understand what's involved in reactions. Everybody thought in terms of mass in those days, or volume of liquid, whatever the case may be. And when something went wrong, their engineers couldn't fix it because they didn't understand that the reaction is not mass to mass, it's moles to moles. It's numbers of atoms and numbers of molecules. And Avogadro, with his hypothesis, gave them a handle on that problem. Have I described that in this class before? What Avogadro said, and this is derived from his law, is if you have two gases and they're confined within these two separate containers, if the volume of this one equals to the volume of that one, and the temperatures are the same, and the pressures inside are the same, then there must be the same number of moles in each one. Now that we know how to relate numbers of particles of each, the difference between the two can only be mass. Right? If they're two different masses and they're exactly equal numbers of particles, then the only way that that can be different is if each of the particles is different masses. Now you can relate the masses of two different. Yeah. So if you have, let's say, neon in this one and helium in this one, under those conditions, we know that the ratio of this one to this one is due to the mass units for each. And that would be about 5 to 1. This would be 5 times as massive as that one.
it's different.
Mhm. Okay, so that was Avogadro's hypothesis, but it was he wasn't too keen on publishing it, or he didn't publish it in the right places. So a student of his, who was no longer a student, but he was out on his own and teaching. Okay, we're up to Avogadro's law, which discusses the relationship between volume and the amount of gas, the number of moles. I was describing earlier that if you know these four factors, pressure, volume, temperature, and moles, you can completely describe a gas, except for its chemical behavior. This is physical only. So I was talking about the problems they were having in manufacturing in Europe in the middle 19th century. And they all gathered together at this little college in southern Bavaria called Karlsruhe. And they decided, we're going to get together, we're going to put our heads together, and we're going to solve this problem, because their manufacturing processes were going screwy and they couldn't fix them because they didn't understand how chemistry worked. They were just thinking mass, mass, mass. It was actually moles, moles, moles. It's numbers of atoms and numbers of molecules that matter. And Avogadro's hypothesis solved that problem, but he didn't give it to them. A student of his, Cannizzaro, had put together his own, published his own lecture notes for his chemistry students, and made a book out of it. And he was handing out copies. It was a small book. He was handing out copies at the as people were leaving Karlsruhe. He also addressed the group in a plenary session. But they politely took his copies and went back to their respective universities and companies. And some of them actually read it and tried to make sense of it. And light bulbs started going on all over Europe. This solves everything. Now we understand what's going on. In fact, I painted myself into a corner. Mendeleev gave Cannizzaro and his publication credit for the way that Mendeleev put his periodic table together, because not only did he arrange things by increasing mass, but he also put them together by their behaviors. And now he knew that the reason they were behaving the way they did was because there were numbers of atoms involved in reactions. Okay, so this was Avogadro's law. It was it was a direct relationship. Initial volume, initial moles of gas. If you change one of these, you change the other one proportionally. That is, if this is equal to a constant, then if you make that one go up, this one has to go up. That's the way quotients work. If they're equal to a constant, you make one go up, the other goes up, or vice versa. And then afterwards, the before and after situation, that's also equal to a constant, the same constant. As long as you don't change any conditions, you don't change the temperature, you don't change the pressure, then these two conditions are equal to the same constant, which means they're equal to each other. And that way, if you know the before conditions and you know one of the after conditions, you can solve for the fourth one. Or if you know the final conditions and you know what you started from, you can, it's like any equation. If you've got one unknown, you can solve it. And we don't, in this class, I know in math class they do, but in this class, we only deal in one unknown. We don't solve simultaneous equations for 2 and 3 unknowns. Okay. So there you get different arrangements that you can make, and I'll just make the point here without spending a whole lot of time on solving it, that you can relate these laws also and eventually to balanced equations, especially if the equations are all gases, right? This is the Haber product. Well, actually, this is the reverse of the Haber process. We take ammonia, we can decompose it into nitrogen and hydrogen gas. Fritz Haber and I forget the guy's first name, Bosch, refined his process. They were the ones that allowed Germany during World War I to take nitrogen from the atmosphere and combine it with hydrogen and make ammonia. And then they converted the ammonia into nitrate. And that's what they used to make explosives. The world had boycotted Germany, and they couldn't get hold of natural nitrates, which were primarily from Chile. Meters and meters thick of bird guano accumulated over centuries was their source of nitrates. And Haber and Bosch put this process together where you took this one and you reverse and made ammonia. Anyway, that reaction can be characterized in terms of gas volume, temperature, numbers of moles. Numbers of moles here, the relationship is 2 moles of this equals 1 mole of that, 3 moles of that. So 2 moles makes 4 moles during that reaction. And that's this part of the equation, Avogadro's equation. So what effect does that have on the volume? Well, if you increase from 2 moles, if you double the number of moles, you double the volume. Okay. I made a point earlier when we were talking about Charles' law that when you're working equations, this temperature has to be converted to Kelvin. It can't be Celsius because negative values in these equations screws everything up. They always have to be positive values. Positive pressure, positive volume, that they're given. Positive moles, that's a given. But temperature could be negative. If you stay in Celsius, that means it has to be converted to Kelvin. Okay. Now, before we get to the ideal gas equation, I wanted to introduce the combined gas law. If you take these gas laws and put them together, we can develop an expression that is useful in all situations, before and after situations. So if you have Boyle's law, let's see, we're not on that one anymore. If you have Boyle's law, you've got pressure and volume. Initial equals pressure final, volume final. That's Boyle's law. And Charles' law introduces temperature. Right, these two. And then Avogadro's law introduces moles. So that's how we got to the combined gas law. And all you have to do is hold 2 of these constant. Like hold these 2 constant, you get Boyle's. Hold these 2 constant, you get Charles. Hold these 2 constant, and you get Avogadro's. So that's all these statements say. Now for the ideal gas law. These individual gas laws or the combined law are good for before and after situations. If you know the conditions before and you make a change to it, to an after condition, then you can relate them with these laws. But suppose you're given a state condition. What is it right now? What do you do with that? Well, you need the ideal gas equation. And that just says that if we take, I shouldn't have erased that, pressure, volume, moles, and temperature. If we fix that as a constant, like we did before, that's equal to a constant, which is equal to the after. Then we rearrange that equation. Leave that constant there. Okay. And this constant now, if we evaluate that constant with values in here of atmospheres, liters, moles, and Kelvin, now this has a definite value. and we give it a new variable R. So PV equals nRT is the ideal gas equation. Oh, I was going to talk about, excuse me, I'm getting ahead of myself. Hold that thought. What's an ideal gas? Okay. We have to contrast ideal gases with real gases. We have to understand that an ideal gas is just that. It's ideal, and real gases vary from that, depending on the conditions. An ideal gas stays a gas at all pressures and temperatures. It doesn't matter how much pressure or how cold you get it, it's going to be a gas all the way down to absolute zero. And point molecular volume, which means what? In mathematical terms, remember when you're talking about dimensions, that has no dimensions. It has no width, no height, no depth. It's a point volume. That's what we assume for gases. If you have one dimension, then you have length. If you have two dimensions, right, and three dimensions go into the board. And these gases do not interact with each other in any form or fashion. They just act like billiard balls when they hit. They just bounce off each other. And of course, they have to obey all the gas laws. All right, that's an ideal gas. Now, what's a real gas? It deviates. Gases do liquefy, and some of them solidify. Like I was mentioning, dry ice. That's solid carbon dioxide. They do have volume, both at atomic or molecular volumes. And they do interact. In other words, when they come close to one another, they might repel, they might attract, or they might react. And one that we didn't mention up here was they interact with the walls of the container. In other words, each gas molecule or atom has kinetic energy because it does have a mass. So when it strikes the walls of the container, it imparts some of that energy in the form of a force. And that's what we use to measure, that's my phone. And that's what we use to measure the pressure. Because if you stick a device in there, instead of hitting the wall, it hits the device, and we register that as a force against some sensor. Okay. Now, fortunately, most gases behave ideally if the pressure is low enough and the temperature is high enough. So what does low pressure mean? Well, 1 atmosphere is low pressure. High pressure would be like 50, 100 atmospheres, even more. So what significance is that low pressure on ideal behavior? Well, low pressure means there are not that many molecules in there. So you don't have a chance to interact with a lot of molecules. High temperature is also low pressure, high temperature. So what effect does high temperature have? Well, if the molecules are high temperature, that means they're moving really fast, because temperature is a measure of the average kinetic energy of all the molecules in the container. So if they're moving at high velocities, then any interaction they have is negated by that force of impact. Okay, so low pressure, high temperature, you will get ideal behavior. And high temperature is room temperature, right? Relative to what? Absolute zero. Right? So 293 degrees Kelvin is room temperature, roughly. Okay, here's the ideal gas equation. It was first conceived by Emil Clapeyron, and we might talk about him later. It's neither here nor there. But there's the formula, PV equals nRT. And this is the one you use if you don't know before and after conditions, if you just know the state right now. If you know the pressure right now, you know the volume right now, you know the temperature right now, you can calculate how many moles there are. And this way, we can use that equation to tell us how many moles are actually part of the reaction or a product of the reaction. That's one example. But it's very important, since this constant now has a definite value, that when you use this equation, the units of measure here are the same as inside the constant. So one constant that we use occasionally is this one. Let's see, 0.08. 206, I think. Liter atmospheres per mole K. So that means that your volume has to be in liters, your pressure has to be atmospheres, moles, and K temperature. There are other expressions of R, in which case you've got to be sure that the other variables match those units. Otherwise, it won't work. Okay. So when you're solving a problem, you ask yourself with gases, is this a before-after situation, or is it a state function right now? There's another example. See, this is the one I just used. This is the one, you would use this one if your equation is interested in energy, like joules, right? If it's a heat equation, then you would use this one there. You're going to see R in lots of places. Okay. Those are just various expressions of the ideal gas equation. And really all you need to do is just say, all right, what do I know? Maybe I know this one, this one, this one, and that one. Then I can solve for that one. You don't have to go to all the trouble to solve for the unknown and then plug in the numbers unless you want to. That's fine. It works. If you need to go, go ahead. I'll finish the discussion. Okay, so in this case, minus 15 degrees Celsius has to be converted. So how do we convert Kelvin and Celsius? Well, 273 plus whatever Celsius is Kelvin. So in this case, we'd subtract 15 from 273. And that would be Kelvin temperature. Let's see. Let's move on. There are problems like this that you can solve in the review document. And we'll talk about it next week in a review session. Up to this point, when we have a balanced equation and we're doing stoichiometry, initially we started off with mass, 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 and converted to moles. And then we went to solutions, correct? Did we do solutions? Molar concentration. We didn't do that. Or mix two solutions together and make a precipitate. We didn't do that yet. Okay. But in any event, when you have a balanced equation, you can't move anywhere in that equation unless it's moles. Right? And this is one of the ways that you can find moles if you know the conditions, pressure, volume, temperature, you can find the moles. So if you're given these values, liters, pressure, temperature, you can calculate how many moles of oxygen are produced because it's the only gas. See? And then you can work backwards if you need to. What's the question here? Calculate the mass of HGO. Yeah. So if it produces these conditions, then you can work backwards to find out how many moles of this and then convert that to mass. Okay. All right. So we found out this many moles of oxygen, and we did the stoichiometry. converted it to moles of mercury 2 oxide. And then this is the molar mass. So then we find out the mass of mercury 2 oxide is 1.87 grams. Okay. All right. I think we are going to do this one this year. Use the Dumas method to determine the molar mass of a volatile compound. I'll give that one to you later. Or you can look in Blackboard. Yeah, it's there. And we're going to use this ideal gas equation when we put a known mass. Well, actually, we fill up this container. There's our liquid, and we heat it at a known temperature. Fill this container up with the gas, and we know the mass of the container, and then we weigh it afterwards, and we know the mass of what the gas that was in there. So we know that mass, and if we're going to do molecular weight, then we know mass per moles. So the moles comes from the gas equation. We measure the volume in here. We know the temperature, okay, because we put it in boiling water, temperature, and we know the pressure because we get the barometric pressure from our barometer. And we know those three. We know R. We can solve for the number of moles. Now that we got both of them. That's the Dumas method using the gas equation. All right, this is an example. Actually, this is an example where we combined equations. We combined the ideal gas equation and the equation for molecular weight, so that we could do the calculation all at once. That's a little algebra. Okay, let's see. All right, we're gonna have to skip this one, I think. Yeah, we're gonna skip this one. I want to get on to one other discussion before we go too far, or before we run out of time, any more than we already have. Let's see. So when you're solving problems in gases, you have to ask yourself this question, among others, is it a before and after situation, or is it a state? You look at the values that are given you. Can I use a before and after, which is simpler actually, or do I need to use the ideal gas equation? And then you got to check to be sure your units are in agreement with the constant. If they're over here, the only one that has to be changed, if it's before and after, the only one that has to be changed is temperature. You can take volume in any volume before and after, can be any units, pressure can be any units. Moles, well, moles is given. But temperature has to be Kelvin. All right, let's see. Dalton's law of partial pressures. All right. John Dalton, the same one that came up with the atomic theory, also came up with this law of partial pressures. He just said that when you measure the pressure of a mixture of gases in a container, the total pressure, it's actually equal to the partial pressures of each of the gases that are in that container, on out to however many there are. The law of partial pressures, that's all it says. The total pressure is equal to the sum of the partial pressures of each of your gases. Okay, and each one of these can be converted to right? If it's PV equals nRT is our gas equation, then each one of those pressures can be written as nRT over V, right? And they just go in here, each one of these. Right? So for each gas, you have a certain number of moles of each gas, and they're all at the same conditions, right? Same R, same temperature, same volume in that container. So actually, the only thing that's changing is the number of moles. So the pressure is proportional to the number of moles. And if we factor out, see, we're going to do that. Yeah, if we factor out this term and just keep the number of moles here and factor out that term, then we notice that the total pressure is proportional to the total number of moles. And our expression for that relationship between the total and individual numbers of moles is the mole fraction. So it's the number of moles of the individual gas divided by the total moles. And it's always less than 1. I mean, if it's equal to 1, then there's only 1 gas in there. You can do that for each gas. And the sum of the mole fractions is always equal to 1. And the mole fraction will also tell you the pressure of each one. If you know the mole fraction times the total pressure, that gives you the pressure of each one. So there you have an individual equation for each gas. And you can relate them in terms of the pressure of the individual gas divided by the total pressure is the mole fraction. So you can work it backwards. Instead of doing it this way, you can do it that way. Okay. I wish we had time to spend on this, but this is just nitroglycerin exploding, producing carbon dioxide, water gas, nitrogen, and oxygen gas. You're going from 4 moles here to 29 moles there. So it's a massive increase in the number of moles, which means you either expand the volume at a constant pressure, or if you confine it, then the pressure is going to go sky high really quick. That's the explosive force of nitroglycerin due to that right there. And a slight increase in temperature. So this is a sample problem that we worked out. We're finding the final pressure with all these other conditions given right here. Here we go. So if we start off at 20 millimeters of mercury, which means that vessel was partially evacuated, and then we exploded it and we ended up at 297. So it was almost 15 times increase in pressure. Okay. And each one of these partial pressures can be determined from that formula. The total number of moles is 29 moles of gas. If all of this is converted, then you've got none of this gas left. Okay? So the total moles of gas is here, and the individual moles is here. So ratio the coefficient with the totals, and you find that the mole fraction is here times the total pressure. This is the pressure of each one of the gases in that vessel. Okay. Now for the theory, why does all this stuff work? And the best theory that we have up to this point is the kinetic molecular theory of gases. It's really simple, actually. It just says that gases are made of large numbers of particles, atoms or molecules, or a mixture of the two. Large, very large numbers. Even though they're spaced widely apart, a small sample of gas gives you billions of molecules, large numbers. Their particle size is very small compared to the distance between them. They're in constant rapid motion, right? I don't know if I did a calculation here, but I have done one. And at a given temperature, those gas molecules are breaking the sound barrier. Only they do it in short distance before they smack into somebody else. They're in rapid motion and they're colliding with each other. They're also colliding with the walls of the container. That's why we can measure pressure. If they didn't do that, then we'd never know they were there because we couldn't measure the pressure. And all gases, no matter what kind of gas it is, inert gas, molecules, whatever, they have the same average kinetic energy at any given temperature. So if you have, let's use the example I used before, helium in one container and neon in the other container, then at the same temperature, they're going to have exactly the same kinetic energy, average kinetic energy per molecule. So if helium, let's see, one isotope of helium would be 4, and neon would be 20, I think. Weight is 5 times as massive. So if we use this equation, right, for the kinetic energy, then if their kinetic energies are equal, but their masses are different. Right? If this mass is 1/2 some m, and velocity squared is equal to this one, neon velocity squared. Right? How do you get those to be equal? Well, if the mass here is less than that one, then the velocity has to be higher. Okay. So we know that with equal kinetic energies, that this one is moving, let's see, the ratio of mass is 5 to 1, and the ratio of velocities is squared. Then in order to maintain the kinetic energy, these would have to be moving 25 times as fast as those. 5 squared. Okay. And again, we have to assume that there's no intermolecular interactions. In other words, when they smack into each other, it's like a billiard balls. They just bounce off. Transfer energy, conserve momentum, you know, all those physical laws. Okay. And I might as well finish it. When we speak of these molecules banging into each other, we need to simplify the expression and use a macro example to help us understand what's going on. So in this case, we'll take 7 balls, each weighs 5 kilograms, like a bowling ball. So what's the average bowling ball? 12 pounds, is it? 14 pounds, I think, something like that. So that's about 5 kilograms. And if we have, I went too far. If we have these 7 balls and they have different kinetic energies because they're moving at different speeds. Remember we said the average kinetic energy for all the molecules is equal at a given temperature. But we know that each one is different. So if this one's moving at 10 meters per second, we increments of 10 up to 70, then the energy of each one can be calculated. Kilogram meter squared per second squared, right, would be 1/2 mv squared. M is kilograms, and velocity is meters per second, but we square it. So kilogram meter squared per second squared. And that's actually a unit of measure called a joule. Okay. So here's our array of energies. So we're going to take the average. Well, we're going to take the average of the velocities first, and that's 40 meters per second. And then we use this one to calculate energy, calculate speed based on average kinetic energy. So if we do that, the average kinetic energy is 5,000 joules. So the average of this is 5,000 joules. If we plug that into this formula with the mass of 5 kilograms, here we go. There's 5 kilograms. There's the mass. There's the energy, joules. And this rearrangement gives us velocity. So what's the average velocity based upon this average energy? And as it turns out, it's 44.72 meters per second, not 40. So what gives, right? We can't use the average velocity to calculate energy because it'll give us a low estimate. This is the actual energy, average energy. So we need to use this value. Well, what's the relationship here? Well, we use a technique and a calculation called root mean square. If we take the root mean square of these velocities, it will give us that value right there. So what does root mean square mean? Right. Well, you work backwards. You take the square of each one of these, like 100, 400, 900, 1600. That's the square part. And then you take the mean of those values, the mean of all those squared values. And then with that mean, you take the square root of it. And that will give you 44.72 meters per second. Okay. Then now we can use that to calculate the average energy. Okay. Now, have you ever heard of root mean square? You may not have heard of it, but you use it every day. Power coming out of the socket is alternating current, which means 60 times a second, it goes from voltage. It goes from a high voltage down to 0 and back to a negative voltage, back up 60 times a second. So we can't use alternating current to do calculations in physics. We need an equivalent to direct current. And the equivalent to direct current is to take the root mean square of all those values. And the root mean square is 120 volts. So that's why they say it's 120 volts, when it's actually, it goes up to like 150 this way and 150 this way. But the root mean square is 120. Okay. So let me see if I can finish this thing up. Let's see. Am I going to need this to complete the discussion? Where's my copy? There we go. I just want to see where I'm headed to this thing. Yes, we do need this. This is a segue into Graham's law. Okay, the energy for each particle. If we could track every particle in the gas, then we could say that the energy of the particle is due to its velocity on the 3 axes. Right? This is called vector analysis. In other words, this particle is moving that direction, But on a framework, a three-dimensional framework, it's moving a certain velocity this way, and a certain velocity that way, and a certain velocity this way. And that's what these three are, X, Y, and Z. For a mole of those particles, right, we would have this value. On average, you would have these vectors would be the sum of the energies for each one times this many moles. So the total energy would be that. But the root mean square of those velocities is equal to square root of the mean of the squares, just like I showed you earlier. That's what this says right here. Right? We take the square of each one, and then we take the mean of those squares, and then we take the square root. That's the root mean square, and this mu is actually the proper variable for velocity on this scale. So, to make a long story short, the root mean square velocity for particles is related to the temperature and their molar mass, molecular weight. Okay? And we take the square root of 3 times, this is the gas constant, times temperature, divided by molecular weight, and that's the root mean square velocity. Okay, and we use this value for R because it has the energy term in it. All right, so what's the average velocity of air at 37 degrees? Well, we need a molar mass average for air, right? Taking into account nitrogen and oxygen as the dominant molecules. So we determined that its molecular weight is this many grams per mole. But remember that R value, go back if I can, here, is in terms of joules, which is kilogram meter squared per second squared. So we have to have velocity, molar mass in terms of kilograms per mole. Now, if we substitute those values, we find out that the average velocity of air at that temperature at 37 degrees, which is body temperature, 37 degrees Celsius, is 500 meters per second, or breaking the sound barrier. I think, what's the 600, or is it, no, it's closer to 700, isn't it? Miles per hour. It's the sound barrier at sea level. Okay. So what if we substitute helium here instead of, so use helium there in this calculation instead of air? Then we find out that helium has to go 1,300 meters per second to have the same energy. Right? So it's just like I said before, the lighter molecules have to move faster. And that's why when you suck helium, the pitch of your voice goes up because the molecules are moving faster.
There's a gas that can make your voice a lot deeper too.
Yeah, I never thought of that before. Do you know which one it is?
I forget, it starts with a B.
Starts with a B. This must not be a pure, not an element.
I can't remember. It's been a long time since I heard the name of it. They had to do a handstand to get it out of their lungs.
Let's see. Hold on a second. Air, okay, 29 grams per mole. So if we had argon would work, it's heavier. Krypton would work too. But it's probably molecular. I bet it is. It's molecular. But it needs to be a larger, a higher molecular weight than that in order to do what you're saying. Okay, Graham's law. Sometimes it's called Graham's law of effusion, sometimes diffusion. It uses this kinetic molecular theory of gas and the calculations that we just showed you, the relationship of velocity to root mean square and temperature and molar mass to compare gases. And what Graham's law says is that, and this is a derivation, I'm going to skip through that. The ratio of the velocity of gas A to gas B is this value for A, just like on the previous slide, and this value for B. And the difference here is the molar mass of the gases. So we can compare the molar masses of the gases. If we have a known gas and we make the comparison between an unknown gas, we can determine its molar mass, right? Remember when we were doing calculations for empirical formula and molecular formula, we needed to know the actual molar mass of the compound. This is one way to get it. Without even knowing what the compound is, doesn't matter. As long as it's a gas, you can compare it and find out what it is. So, how do we measure the velocity of one against the other? Well, one way is, especially if they will react with one another. I'm going to skip through this and show you the example. Here we go. In this case, we have hydrogen chloride gas and ammonia. And we put one in one end and one in the other. Well, one's heavier than the other. So which one's are they gonna meet right in the middle? No, because they're moving at different velocities, right? So the lighter one's gonna go further. And I think the lighter one is ammonia. And when they meet, ammonia and hydrogen chloride form a cloud. It's a suspended solid, ammonium chloride. And you can see it right here. So the ratio of the distance here is the same as the ratio of the velocities. And if you ratio those two together, well, in this case, we've got an unknown. We're using Graham's law. So the distance traveled for ammonia compared to the distance for X is this value. 2.738 is the ratio of those distances. And we use that ratio to find out what the molar mass of X is. Because notice that this one's in the numerator, that's in the denominator. And we can find that the molar mass for our unknown is 127 grams per mole. Okay, and if we have a selection, we think it's pretty close to this one, hydrogen iodide. Okay, let's see. This process, this Graham's law was used. Yeah, we're near the end. Graham's law was used during World War II as a way of purifying uranium and concentrating it enough of the U-235 to make a weapon. So how they did it was, since U-235 is lighter than U-238, Graham's law says if you try to push it through a sieve, very small holes, then, and they had to convert it to a gas, so they converted it to uranium hexafluoride. Right. These are both gases at a given temperature, and to be elevated temperature. Then through one filter, you would enrich on the other side in this. So you just stack the filters together, right? And then you keep sucking off portions of this one and running them back through again. And eventually, you increase the concentration here to greater than 90%, so you can make a bomb. But as you might guess, it takes a lot of filters, I mean, massive numbers of filters. because this is only 0.5% of the total of naturally occurring uranium. So I used to live in Oak Ridge, Tennessee, and they had 3 plants there built. Oak Ridge was the center of research in nuclear technology during World War II and afterwards. And they built this huge plant called K25. And most of this is taken up with those filters. And besides that, they had to make the filters out of a material that was not corroded. But this compound is extremely corrosive. They couldn't use stainless steel or any type of alloy. So fortunately, DuPont had come along and invented Teflon. And it turns out Teflon is impervious to this stuff. So they made their filters out of Teflon. And my family wasn't real rich. So when we needed entertainment or a break, we just all, kids and all, piled into the car and we drove around these plants. They had barbed wire fences around them. And it took you 15 or 20 minutes to drive around the thing. As long as you didn't cross over the fence, you were good, because they had shoot first and ask questions later. But they had other plants, not just this one. They had the magnetic sector. You know, they charge the molecules and fire them through a magnetic sector, and the heavy ones would come out here and the light ones would bend a lot. And then they had ultracentrifuges, like Iran is using now, gas centrifuges. And they had stacks and stacks and stacks of those. So they had these massive plants built to figure out which one was the most efficient. And money was no object. I mean, we were fighting a war. So the government just, printed money and built this stuff. Okay, real gases. One last one. The PV equals nRT is the ideal gas equation. But if you're going to be working with gases as your profession, and the conditions are going to be ranging wide, very low temperatures, very high pressures, then you're going to have to compensate for those real gas effects. And this is the equation that you would use. Based on the real gas, Emil, I think his first name is Emil, van der Waals, proposed this equation. Oh, excuse me, Johann Dieterich van der Waals. I just gave him a new name is all.
He's got about 15 names.
Yeah, his friends called him Emil. No, I don't know. But his work with gases got him a Nobel Prize in Physics in 1910. So this is his expression. See, there's a volume term, there's the pressure term, and there's nRT. So correcting for the pressure differences required this term, and the correcting for the volume differences was this term. And you had to experimentally determine this A value and that B value in order to make the corrections. Okay, that's it.